Good afternoon, everyone. In this video, I'll continue the discussion about system design decisions. I'll be talking about management of data storage and handling global resources. So, coming first discussing about management of data storage is concerned, there are different alternatives for data storage in applications. One way is like using data structures, or the files, or the databases. Data stores actually provide different trade-offs, okay, among cost. Okay, so in one of the approach, like the cost may be pretty high. Say for example, for databases, you have to buy them, okay, from a vendor, or like access time, in which way like you can actually access them quickly. Okay, data structures you can access them quickly because they are in the memory. Okay, the capacity how big we can actually handle. Say for example, data structures, all of them you cannot store them in the memory. Okay, that would be a problem. Okay, and reliability as well. Okay, so basically like some of them are very reliable. Say for example, databases are extremely reliable. Okay. So in that sense, like data stores actually provide different trade-offs. Okay. We can use these data storage solutions separately or in combination in applications. Okay, uh, so we can use them either individually or in combinations. Okay, so you can have two of them used in a particular application. Say for example, a desktop application, something like a personal computer based application, may use memory data structures and files, both of them in its application. So let's look at these approaches, okay, one after the other. Of course, like in terms of the data structures, I already talked about. They are stored in the memory, and then like they will be actually accessed directly in the applications. Say, for example, in the desktop applications. Let's look at the next approach. Okay, next data store solution, which is files. Files are actually very cheap. They are very simple, and then like you can permanently store them. Okay, so file system, literally almost all the operating systems actually provide you access to them. But the problem with them is like file operations are at low level. Applications need to provide like additional code to basically provide a suitable level of abstraction. Okay, so that is one problem with them. Um, and also like file implementations vary for different computer systems. Okay, even for operating systems, like how basically like the files are stored and what is the end of the line, there are differences even between Windows and Linux based systems. Okay. But if you are developing a portable application, you must carefully isolate these file system dependencies. How you actually handle them, and then like how the file structures are organized. You have to take care of all those things. Okay. Implementation of sequential files are mostly standard. Okay. Say for example, the general way like you are storing the files, like you will have a sequential access of the files. Okay. So most often like their implementations are standard. Okay. You don't have to worry much about them. Okay. But commands and storage formats for random access files, say for example, you have to change some input in the middle of a file, okay, so and then like you are regularly doing those things, so those are random access files. Okay, so commands and storage formats for random access files will be different, they may be different. Okay, at the same time like indexed files will also be different. Okay, so the data that is nicely suitable for way in, so that like they can be stored in files or something like these things. Okay. Data with high volume and low information density. You have a lot of files, but the information in them is relatively less. Okay, so for example, like archive files or historical records or logs. Okay, so you will be storing them in files. Later, when you want to extract some information out of them, you will be sequentially reading all the files. Okay, so for such a thing, such information, the best data store solution is files. At the same time, like modest quantities of data. Okay, so not very big, not very small either, with simple structure. Okay, its structure is not so complicated. Then again, like you can use the files. Okay, so we have tried these things in the labs as part of the Java exercises as well. Okay, we have seen, okay, how to be able to store certain structural data as well into the files. Of course, as I mentioned, like data that are actually accessed sequentially. Okay, files are very good for that. Okay, and most often it is also assumed like once you are trying to read a file, like you can actually load the complete data into memory. Of course, like when the files become really big and then like you have to handle, like you cannot process on a single machine, you have to process at distributed clusters. Okay, so then like that's a different aspect. Okay, even there like the data is actually stored in files, but then like processing happens like distributed data processing. In most general cases, like it is not like that one. You can actually read the complete contents of a file into the memory, and you can actually sequentially read through it, and then like you can either modify, change, or do something or add something. Okay, or read the data and then like do certain other processing. That's where like files are actually useful. Then the other data store approach is these databases. Databases are actually managed by database management systems. Okay, different vendors provide different types of database management systems. So there can be relational database management systems and object-oriented database management systems. Okay, what they are, I'll quickly talk about them, but then like it is a complete subject on its own. Okay, but in terms of the system design, you should be already planning like what sort of database management systems are like data storage, like which you will use for that particular application. In that context, like we are actually looking at, okay, looking at these things. So with respect to this DBMS, okay, so frequently accessed data is actually cached into memory, okay, by the DBMS. So why we do it? In order to primarily achieve this best combination of cost and performance from memory and disk storage. Because the point is like, say for example, storing everything into the memory, it is pretty costly because like you have to load several other applications. So the memory, okay, so if you put it, then you have to replace it as so and so. But at the same time, like if everything is stored on the disk storage, okay, so you are trying to access the data a lot of times, and every time like it has to go to the data storage, read it and populate it and then like use it. Okay, so some trade-off has to be considered there. Okay, and then for that one, like DBMS is basically cache the data. uh, Database management systems actually make the applications easier to port. Okay, but their interfaces are generally complex. Okay, say for example, like each database is like how you actually invoke them. Okay, in your applications. Okay, you may have to use uh, different drivers and all sorts of things. So the development of a database based applications is a little bit complex. Okay, the data that is actually suitable for databases. Okay, so here are some of the examples. Say for example, if you have large quantities of data that must be handled efficiently, then databases are good. DBMSs are good for that one. Okay. At the same time, like data that must be accessed multiple by multiple application programs. Say for example, there is certain data which is existing in databases, and then like you have multiple applications, desktop applications, interactive applications, okay, network-based applications. Okay, all of them are trying to access the same data. Okay, then databases are very good for that one. They can actually handle this sort of concurrency. Data that require regular updates at fine levels of detail by multiple users at the same time. The same example which I have given for the earlier case also fits here. Assume like there is a huge store is there, okay, a shop is there which is actually maintaining all its products somewhere, and these different applications, the desktop applications, these online applications, the web-based applications, how to regularly access that data. Okay, then again, like databases are good for that one. Again, data that requires coordinated updated via transactions. Say, for example, multiple users can access it. Okay, and if certain transaction has to be done, it has to be coordinated. Then again, DBMS are very good. Okay. Say, for example, simple thing like if there is a bank database, the same example which we are always talking about, the ATM case. Okay. Say, for example, okay, so for example, one of the customer is trying to, okay, so for example, trying to access from the ATM. Okay, at the same time, like okay, the same data is being, say for example, some for some other transaction which the bank is doing. Okay, so it is also doing in the middle. So these transactions are to be basically coordinated. Okay, say for example, like you basically put some money, you deduct some money, put some money, deduct some money in a particular day. At the end of the day, like all the transactions are to be committed. So there should be some coordinated way of handling it. Then DBMSs are very good for that. at the same time, like if the data is to be long lived, okay, so it has to be there, okay, so you have to store it for pretty much long time. And if the data is highly valuable for an organization, databases are good for that one, okay. And again, like the data must be securely accessed, okay, so and then like unauthorized access and malicious attacks are to be prevented. Again, like you need a system which actually manages all the things properly, okay, so databases and dbms are very good in such cases as well. So in terms of the types of database management systems, okay, so I already talked about there are different types, something like relational database management systems, okay, object-oriented database management systems, some of the advanced concepts like non-relational database management systems are also there, okay. So discussion of all these things as part of this video is beyond, okay, beyond scope, okay. So if anybody is interested, you can basically start checking those things. But in general, like relational database management systems actually store the data in terms of tables. Okay. And there are a lot of different RDBMS solutions that are possible. And actually, these are the solutions which actually dominate the marketplace. Okay. Say, for example, Oracle database or like MySQL, etc. Using RDBMS, you can also have good implementation for an object-oriented model. Okay. And for most of the applications, you will be actually using RDBMS. RDBMS are sufficient for those purposes. Okay. As I mentioned, like object-oriented database management systems are also existing. In this case, like the data is actually represented and stored in the form of objects. Somehow, object-oriented data DBMSs, okay, database management systems, have not become very popular in the mass market. Okay. Some of the reasons can be like RDBMS has this SQL as the standard query language, but object-oriented databases do not have such a standard yet. Okay, there are some. I mean, like there are some advances which have gone there, but then like still they are not fully accepted in the mass market. Some of the well-known examples here are like cache, concept base, DB for objects, etc. DB4O. Okay. And the applications that actually use these object-oriented database management systems are also a little bit tricky. Okay, so uh, some of the applications where they are used are like, say, for example, in real-time systems, okay, and architectural and engineering for 3D modeling, okay. So and telecommunication applications, pure scientific applications, something like molecular science, biological sciences, astronomy. At that scale, like object-oriented DBMSs are actually used. So that's about data stores, and you should always, for your particular application, like you have to actually decide like which of the data stores you will be using. But at the same time, as I said, like you can use multiple types of data stores in a particular application. Okay, there are no problems with that one. Then the next step in this, the decisions you have to take during the system design are these global resources. The system designer must identify global resources and determine mechanisms for controlling access to them. There are different kinds of global resources possible. The first one is the physical units. Say, for example, you can have different processors, okay, different tape drives, okay, so magnetic disk, you will store them somewhere. Okay, these are all the global resources which can be accessed by multiple applications, okay, uh, from the same organization or over the internet. And these global resources are somehow are to be properly controlled. Okay, say, for example, access to them is to be properly controlled. The physical units, say for example processors, how you basically use them, okay, tape drives, how you access them, they're all challenges, okay, so we have to look at solutions for them. So the other kinds of global resources are space, say for example disk space, which you will be using for storing the things, okay, or like a workstation screen. Say for example, if multiple applications have to use this desktop screen, okay, how do they actually share the resources, okay, how do they basically access those this screen space, okay. So for the ATM case as well, like say for example it has that keyboard, okay, to enter those numbers, okay, for different types of transactions it basically has to, the only way like he can give the input is through that screen, okay, through that keyboard. So other examples are like, say for example, the buttons on the mouse can also be considered as spaces. Okay, so these access to these spaces are to be managed. Say for example, two applications cannot have the same right button clicked at the same time. Okay, so somehow like you have to control the access to them. There can also be these logical names. Say for example, for each object, like you may have to create object IDs. So these are also like global resources. Okay, because like eventually you have to create individual object IDs for each and every object. There cannot be any clashes with the object IDs, and they have to be taken care somehow or other. The same thing happens with the file names, class names. And in the example which we have been considering, the ATM case, okay, so the account numbers. Two accounts can't have the same account number. How do you ensure that? Okay. So controlling access to them is always a challenge. Of course, again, like access to this sort of shared data, we can actually have it through the databases. Okay, examples are the databases. So now, how do you actually handle that? Handling the global resources. If the resource is a physical object, then it can control itself by establishing a protocol for obtaining access. Assume like there is a printer in this room. Okay, so if I have to access that particular printer, it is a physical object. Okay, so it basically follows a certain protocol. Using that protocol, I have to actually access it, and then like say for example, print something out of it. Then the protocol will actually control like how multiple users can actually access to that one, and then like how the synchronization basically taken care of. If it is a physical object, then it is not a big problem. But if the resource is logical, then there is a much bigger danger of conflicting access in shared environment. Say, for example, independent task can be there, which actually can try to simultaneously use the same object ID. Okay, so that's a challenge. How to handle those things? Okay, we can actually have this sort of guardian objects. Okay. These guardian objects actually own these global resources, and that's how like we can actually control access to them. So all the access to a particular resource, okay, so to this global resource, must pass through this guardian object. Then the guardian object actually can control like which of the application actually, I mean like which of the user can actually invoke that or access that global resource. Okay, so guardian objects are good for that one, and you can actually employ these guardian objects for that purpose. So the other solutions are like, say for example, we can also partition a resource logically. Assume like say for example like you have to assign object IDs, okay, IDs to objects, okay, and then like you cannot assign for all the objects which are created by one guardian object. Alternatively, what you can do is like, okay, so you can actually assign subsets to different guardian objects existing, and these individual guardian objects can independently manage the control for those objects within that range. Okay, I'll give you a very simple example. Okay, so for example, if there is a queue which is handling all the people, okay, so everybody is coming in a queue, and then like if there is a single queue, then it would be a problem because like that becomes a bottleneck. Alternatively, what you will do, all the people like who have their first name starting from A to say for example some H or something will go to the first queue. Then I to say for example S will go to the next one, and then T to Z will go to the third queue. Okay, that way like you can have different guardian objects which is actually taking care of that queue. And the same way, like say for example you distribute the objects, okay, and take care like say for example this object, the first guardian object actually assigns object IDs which actually start with, say for example it is randomly assigning IDs. It will start something from A to H. The second object can create object IDs, I mean like the second guardian object can create object IDs which start from this I to say for example the same example yes. The third one creates object IDs from T to Z, and within that guardian object actually takes care like within its own group like the uniqueness is actually maintained. Okay, so that sort of thing we can actually think about. That's how like you can actually partition the resources logically. So the same example is discussed here. To generate object IDs in a parallel distributed environment, we can pre-allocate a range of possible IDs to each processor. If you allocate like that one, then there is no need for global synchronization. You don't have to monitor anymore. Okay, so the ranges are already defined for these guardian objects. So that's the second approach. The first one is like having a single guardian object and all the access going through that one. Okay, all the accesses for all these global resources must go through the guardian object. With the second one, like we are partitioning and then like individual guardian objects taking care of each and every partition. But there are some problems with these guardian objects. In time critical applications, the cost of passing all the accesses for a resource through a guardian object is too high. Okay. Say for example, if a time critical application where you have to get the response within milliseconds. So again, like it is one more level of invocation. Go through guardian object, let it basically ensure that one and everything. There is an alternate solution for that one. You can actually you can employ locks. Okay. Locks actually give the holder right to access the resources directly. So basically, like say for example, if somebody wants to, I mean, like if one of the user basically wants to access that particular resource, okay, so he will first come through the guardian object. The guardian object will assign a lock for it, okay, and the user basically has that lock, so he can actually use that, okay, and then like the next access don't have to come through the guardian object. So the guardian objects will be still be there, but you will be accessing it only once. So that's another approach, okay, having the locks. But remember this always, especially during the system design stage, do not use direct access to shared resources unless it is absolutely necessary. So there are different solutions for that one. Okay, so don't use a direct access. We have already discussed 3 different solutions for that. Use any of them, but never give direct access to the shared resources. Regarding the reference concern, we are still in chapter 14, okay, of this object-oriented modeling and design with UML. Michael Blah and James Rumbaugh. Thank you very much for your attention.